Good evening and welcome everyone to this plenary lecture which is entitled The Astronomical Revolution. My name is Tim de Zeeuw. I'm the Director General of the European Southern Observatory, sometimes simply called ESO, which operates flagship astronomical facilities in northern Chile. And these include the Very Large Telescope on Paranal. It includes the most powerful radio interferometer in the solar system called ALMA, which we operate in partnership with North America and East Asia. And it will soon include the European Extremely Large Telescope, a 40-meter behemoth, for which we had the groundbreaking last Thursday on Paranal, which was widely televised and seen around the world, I believe. Today's lecture is about astronomy. And our speaker is the Nobel laureate, Professor Brian Schmidt. Brian hails from Montana and spent his high school years in Anchorage, Alaska. He got his undergraduate degree at Stewart Observatory at the University of Arizona, and then moved to Harvard, where he got his PhD in 1993, I believe. He worked on supernovae. These are the giant explosions which marks the death of stars, the very traumatic death of stars. He's a world expert in this. And he used supernovae as light beacons to study the distant universe, and in particular to study the expansion of the universe. And he and his team, together with his competitors, made a stupendous discovery in the late 90s, namely that the expansion of the universe has been accelerating over the past 5 billion years. And this got both teams, Brian Schmidt, Adam Rees from one team, and Sol Perlmutter from the other. This got them the Nobel Prize for Physics in 2011, because this is completely ununderstood. It revealed the existence of something that's called dark energy, which pervades our universe, and we would all like to understand what that is. Today's lecture, well, I should also say that Brian leads currently a telescope project in the south. It's called SkyMapper. It makes a map of the entire southern sky to find out what's really there. And perhaps most importantly to note is that Brian also has his own winery, and he makes excellent Pinot Noir. And you might want to question him about this afterwards. Speaking of questions afterwards, I'm told that there is the opportunity to tweet to the hash marks behind me during the lecture, and the most appealing questions may get, at the end of the talk, the opportunity to be answered by Brian. The lecture, as I said, it's called The Astronomical Revolution, and let me just double check something here. It's a plenary lecture, and believe it or not, Brian will summarize for us our understanding of the entire universe. No pressure, Brian. Everything that's in it and how it evolves, and also the role that is played by state-of-the-art research facilities that in particular have been built in Europe. And I believe that towards the end he will also look forward a little bit to the future. So with all of that, I'd be very happy if you gave Brian a round of applause, and I give him the floor. Brian.
All right, thank you very much. It's a great pleasure to be here and address my friends here in Copenhagen. So today we're going to talk about astronomy from A to Z. And I call it an astronomical revolution, but it's one that's still continuing, and I hope to convince you in the course of today's lecture that so much has happened over the last 100 years, and I expect so much more will happen in the next 100 years. But don't have me completely predict what the future is, because I have really no idea. And that's the beautiful thing about science, is we don't really know what we're doing until we do it. So let's start off with some philosophy. Let's talk about science in its purest form. And that's a great place to bring in astronomy, because astronomy really is science in a very pure form. It's quite abstract. So here we have Ptolemy, and he constructed a view of the universe back more than 2,000 years ago that tried to reproduce how planets went across the sky. We call that the Ptolemaic universe, And it was built on axioms, and it was quite complicated. You can see that the planets go in kind of spiral graph, these little loops and turns to explain it. And the reason he had to have the universe do that is that he built up his scientific principles with the axioms, which was the Earth's the center of our universe, and objects travel in circles. And to figure out how Mars would traverse the sky, he had to build up very complicated paths and trajectories. But it worked well, and indeed for 1,500 years, that is how everyone went through and calculated how Easter occurred, for example, or how you might expect to find Mars on a given night. And he was able to build this up, and it was used for those 1,500 years. Then came along Copernicus. Now, Copernicus transformed that very complicated idea, built on simple axioms, circles, and we're in the center, and changed it. He said, circles, we're not in the center. The sun is in the center. And then the orbits of the objects looked like nice little circles, much, much less complicated. Turns out it didn't work quite as well as Ptolemy, but it was a much simpler idea. He wasn't putting circles and circles and circles, just one set of circles. It worked almost as well. Now, this was an idea, but it was theoretical. And it wasn't until we actually observed things, and that came from none other than Galileo, who had a telescope he could use, and he could go out and look at these planets. And what did they look like? Well, when he looked at Jupiter, it was a fuzzy blob, but it had 4 other fuzzy blobs that went around it. Very clearly, Jupiter was the center of that little system. But more importantly, he could look at Venus, and he could see that Venus showed phases like the moon, but it got bigger and smaller, and so when it was behind the sun and fully illuminated, it was small, just like Copernicus predicted, but not at all like Ptolemy would have predicted. Copernicus' vision became reality when we made observations. And that is true of everything we do in science. Science is a mixture of ideas that you make real with observations. So Newton provided a powerful mathematical framework for understanding gravity. It allowed the precise prediction and therefore falsification, and really allowed science as we know it to start. So you could go out and test how this works, but you also needed to know what was out there. And that's where telescopes came along. Herschel was able to go out and look through the sky and find a new object. Object was Uranus. He found it in 1781, and he saw it as a faint, fuzzy blob that moves slowly through the night sky. The first planet discovered since humanity had really started looking at the nighttime sky. But immediately it was realized when you applied Newton's laws to Uranus's motion, there was a problem. Uranus was not moving precisely as Newton predicted. Does that mean Newton was wrong? Maybe. Or maybe it meant, as a French astronomer realized, that it might mean there was another planet, a planet Neptune, that was influencing, and you could use Newton's laws to predict where Neptune was. And he did, and in a very rare form of French-German cooperation in the last century, still rare today as near as I can tell, the Germans were able to quickly locate where this planet was, Neptune. Their reality, once again, became real. We had an idea, which was there was another planet there, but it became real when we observed it. Einstein's theory of gravity then came along when Einstein had a very singular idea, subtle, that acceleration by gravity and acceleration due to moving faster are equivalent. In other words, if you're in a rocket ship speeding up at 9.8 meters per second squared, there was no experiment you can do that differentiates that from just being on a box stuck on planet Earth being accelerated by gravity at 9.8 meters per second squared. A subtle little thing. It took Einstein 8.5 years to solve it. And when he did, he predicted that space had to be curved. And that, for example, if you looked at the sun during the eclipse, as Eddington did, shown at the bottom of that last picture, if you look at the stars in eclipse, they would be moved by the curvature of the sun that it imposed on space. And in 1920, it was realized by Eddington that he could go out and test this. He did, and voila, shown in the headlines of that year, lights are askew because Einstein was able to, in advance, predict something that had not been observed. Newton's reality disappears, Einstein's reality of gravity reappears or emerges. Does that mean Newton's version of reality is wrong? Well, yeah, sort of. But on the other hand, if I'm going to go out and, throw this across the room and figure out where it goes, I promise you I do not use general relativity to figure it out. I use Newton's laws because that is a good approximation. General relativity is useful when you're dealing with black holes, which we'll talk about in a little bit. So reality is a little fuzzy. Is Newton real? Is Einstein real? I would claim they're both real, just depending on how you're using it. And I know Einstein's theory of general relativity is wrong, because it doesn't work well with quantum mechanics. So we're deluding us if we think there actually is a reality out there that you can pin down. You'll never know what it is. And even if we find it, we as scientists will always be looking for how it's wrong, because that is what we do. So what is reality? I say reality is a set of ideas which predict the observations we make. At least that's my version of reality. If you're a philosopher, you may disagree. Let's not talk about it. Don't tweet anything. All right. And the way we astronomers go out and we look at reality and try to understand this crazy universe, as I will show you, that we live in, is through the Hubble telescope. Now, we all possess a telescope, 2 of them typically. It's our eye. But we astronomers use larger telescopes to do better and more interesting things. So larger telescopes collect more light. I think most of us think about that. But they also allow us to observe a wider range of wavelengths than our eye. Our eye can only see optical light. And finally, they greatly improve detail due to the quantum mechanical problems with diffraction. And that's something we don't always think about. So let's look at these in detail. They collect much more light because they have a larger collecting area. The bigger the telescope, you collect more light by the square of the size of the telescope. You could observe at other wavelengths other than optical, but by having detectors that are sensitive. So you can observe things from the radio, where the light will have wavelengths of maybe 10 meters long, and in gamma rays, where the wavelength will be, for example, 10 to the minus 11 meters long. In one case, radio waves, the light behaves as a wave. Gamma rays, they behave more as particles, and that's that beautiful duality that quantum mechanics gives us between particles and waves. And the greatly improved detail is what we call the resolution. If you're looking at something, your ability to make out detail is related to the wavelength you're looking at and the diameter of the telescope. And so if you're looking at things in radio, they're going to be fuzzy unless you have a very big telescope. So radio telescopes, you typically need to be big. And if you have a gamma ray telescope that you could actually focus, it turns out we can't make anything quite like that, you wouldn't need to have it be big at all to get lots of detail. The problem is gamma rays tend to go right through mirrors, and so they're very tricky. You tend to make it through tricks involving pieces of lead and things that just grab anything that hit them. So the Hubble telescope is our tool. So let's just look at this in detail. We have our eye, or some nice person's eye, and we compare that to, for example, the 8.2-meter VLTs. So the VLT is roughly 8 meters across. The eye is roughly 5 millimeters across. So one of these telescopes collects 2.56 million times more light than the human eye. To add an extra factor of 100, they're equipped with detectors which are 100 times better than our eyes. So really, they're about 250 million times better than our eyes are at collecting light. If we look at wavelength, here's a picture of the Milky Way taken with a photograph. And if you look at that in radio, you see something that looks quite different. And that's because the things that emit radio waves are often very different than the things that emit optical light. So what type of detector you use, an FM radio as opposed to a digital camera, actually depends on what you're going to see. Finally, if we think about resolution, our eye being 5 millimeters, let's compare it to the Hubble Space Telescope. Our eye, if you look at Jupiter, it sort of looks like that. Here in Copenhagen, not this time of year probably, it's too dark. But this is what the Hubble Space Telescope sees when it sees Jupiter. And that's because it sees roughly 480 times clearer images than our eye does. So these are the things and the tools that we've developed over the last 100 years to help us explore the universe. So let's try them out. Let's go through and discover planets around other stars. We found all of the planets we think around our own. So if we go out, this was first done in 1995 by the Swiss duo of Mayor and Queloz. And they went out and announced that first discovery of an extrasolar planet, confirmed a week later by an American team. Now, if we go out, this is yesterday's list of planets. There are some 1,700 planets now known outside of our own in more than 1,000 separate solar systems. So there's many multiple systems out there. I like this list. This is from yesterday because I actually helped discover the last one on that list. So I don't just do cosmology. I like doing the things that using the tools. So how do we go out and discover these? Well, Mayor in Switzerland was able to use the fingerprints of atoms, their spectra, which identify each atomic transition, and then couple that to the Doppler shift, the fact that if you're moving relative to the speed of a wave, you get essentially compression of the waves in one direction and extension in the other. And so that if you, for example, look at a planet or a star that is being orbited by a planet, you can detect the motion of the star by the shifting of its spectral lines. So in detail, if we look at, for example, a planet orbiting another star, the planet goes around. Earth's moving at 30 kilometers per second right now. But the star also moves around the center of mass, and that's not a very big motion. In the case of our sun, a few meter per second or so. But if you build and dedicate a facility like ESO has, the ESO 3.6 meter, which was kind of a lousy telescope until they put an amazing instrument on it. And this instrument, known as HARPS, is one of the highest precision instruments I think ever made by humanity, but it's certainly the highest precision one we have on a telescope. And by going through and sucking all the air out and keeping it exactly the same temperature, they're able to measure the velocity of a distant star, thousands of light years in distance, to substantially better than a meter per second. A meter per second is this fast. I'm walking a meter per second right now. And you're able to do that for a whole star, halfway across the galaxy. That is an amazing achievement that humanity has been able to do. And it's allowed them to discover the first object, which without that much precision, but many, many objects. And indeed, this technique has been used to discover a whole range of objects up on this diagram where we plot their mass versus how far away from the star they are. I also put up there our own solar system, and you can see we're discovering objects using this technique where we have, for example, Jupiter. But we don't quite yet have the precision to find things like the Earth, because the Earth doesn't cause enough motion in our sun. So we need probably another technique. This is still a very useful technique, but there are other ways to discover planets. Using this technique, though, around smaller stars, they have been able to, for example, find a system that has 3 or maybe 4 objects 4 planets in the so-called habitable zone, that place where water is liquid. And since we are sure life must be exactly like us, we're pretty sure that if we're going to have something, it must be in that place where water is liquid. Actually, there's lots of reasons to believe that life will occur in that sort of nice area of temperature. And it's also quite amazing that we're finding lots of stars out there that have planets in precisely those areas. But there are other ways, as I said, to discover planets. Here is an image of the sun in 2012 as Venus passed in front of it. You can imagine when that occurred that the sun would have looked a little bit fainter, about 1 part in 10,000 fainter. Imagine if you go out and make observations of lots of stars and look for them to get a little dip in their light. Well, that's exactly what people have done for a substantial time, and the US dedicated a mission known as Kepler to do this, and it found, as I will show you, many thousands of possible objects. It finds these things because it's above the Earth's atmosphere. The Earth's atmosphere is a bit of a curse. It tends to cause stars to look fuzzy so that you can't see them as clear as you might without the atmosphere. And in that fuzziness, you actually make how bright stars appear waffle very quickly over time. Up in space, you get past a lot of those problems. So Kepler has found, and just released some more, which I don't have the diagram of, a whole range of objects, and you can find things that are different. You can actually find smaller planets. So here we plot the radius of the planet, where Earth goes across there, and you can see we're finding now with Kepler many planets that look like Earth-like things. The problem is that Kepler only had a 3-year mission, which unfortunately, normally when NASA says a 3-year mission, they really mean 7 or 8. But in the case of Kepler, it really sort of ends up turning out being about 3. And so you need a lot of time to find things like the Earth. So we're finding objects with shorter periods than our Earth, but look very similar to our Earth. Now, if the Earth was going around a smaller, less massive star, then it would have a relatively short period and still be in the habitable zone. Or you could have an object more massive than Earth, and it would be easier to detect. So the first object that Kepler found inside the habitable zone was a super-Earth. I think these would be kind of a fun place to have. I think humanity would probably benefit right now from a super-Earth. Give us another 50 years to trash the joint. But we are able to find these in large numbers. Kepler has found so many objects that we now know that the average star in our solar system has a planet. Now, the systems, we're not sure all or very frequently look like our own, but we're beginning to get into that regime. Now, when you find one of these things, what are you going to do with it? Well, one of the things we can do is we can go and use one of the ground-based telescopes, shoot a laser up in the sky, and correct for the atmospheric effects. Why would you want to do this? Because that means you can look in at the stars and start imaging the stars, the planets directly. And so you can see here on one of the first systems on the Keck telescopes in Hawaii, when you turn your system on, you essentially get beautifully crisp images, even better than you can take out in space with the Hubble Space Telescope. If you apply it, as ESO has done earlier this year, on a nearby star, you can actually make images, in this case of a young star that has a disk that we think might likely end up eventually producing something like a planet. And in the coming years, I think we can expect this instrument and a similar instrument on the Gemini telescopes in Chile to go out and start mapping out at least some of the planets at large distances. So imagine what you could do if you had a bigger telescope or one that could see in different colors. Well, ALMA, this instrument run by Eastern Asia, the US, and ESO, is a radio telescope that works in this regime sort of that we haven't been able to do before because it's been technically too challenging. We're able to do because computers are fast enough. And if you look at things wavelengths shorter than a millimeter, shorter than what your microwave would put out, it turns out that lots of molecules that occur quite frequently in space have atomic transition or have molecular transitions that put out a lot of energy there. And then you can use the techniques of radio astronomy, which allow you to use computers to combine the signals from telescopes spread out into essentially like they were one big telescope. So it's possible, although your wavelength is quite long, you can make the telescopes much, much bigger, and therefore you get very good resolution. And so if you look at some of these new stars and look around them, you can look at them not just in light, but you can look at them in chemistry. You can actually see what they're made up and how things are coming together for the first time. This is something that's brand new and again is going to multiply over the coming years. But we all want Earth-like planets. How are you going to do that? Well, you need to go out and look at a lot of bright stars. So there is a mission named TESS done by NASA, and Europe is doing a mission called Plato that is just loaded up with little telescopes out in space, looking at all the stars you can possibly imagine for the little ones that are nearby and bright, that have something that looks like Earth. So these missions will be happening towards the end of this decade and into the next decade, and they should be finding many, many Earth-like objects close enough so that we can do some kind of interesting things. Here is a picture of Venus when it was transiting. Now, it's not Photoshopped. This is really what it looked like from the NASA instrument that was taken. And if you see, there's a nice little rim around it, like it's almost like you've done a shadow or something. Well, that's actually light refracting through the atmosphere. And if you were to take a spectrum with a very powerful telescope that has lots of light, you would actually be able to see what was in the atmosphere of Venus when it transited in front of its star. So imagine if you have a next-generation telescope like what the Europeans are building in the case of the extremely large telescope. It's 500 times more powerful at looking at planets than an 8-meter telescope, and you can already see what we can do. So these telescopes, and there are two telescopes, other telescopes slightly smaller, being built at other places in the world or planned to be built, and these things will be coming online again early in the next decade. All right, so let's switch gears and say black holes. Why do we think they're black holes? People always say, if you can't see a black hole, how do you know they're there? So we're going to zoom into the center of our galaxy. And when we zoom in with better and better resolution images taken from typically bigger and bigger telescopes, what do we see? So this is some work done using ESO telescopes from a group in Germany. And this is a movie of the very center of the Milky Way using that adaptive optics. And oops, let's see. Okay, that was a mistake. Now I've just blown the timing for my talk. So we're going to zoom in, and when I'm going to explain, you're going to see these, they're kind of modelly because the atmosphere is not always perfect, even with these adaptive optics. And I want you to look, and you'll see some stars moving. In particular, there's one in the middle that moves very quickly. And the reason it's moving very quickly is it's like a comet going around the Earth. When it gets in close, it moves very quickly because there appears to be something that weighs roughly 3 million times the mass of the sun, but miraculously doesn't emit any light that we can particularly see, at least in the optical. So those observations allow us to reconstruct orbits of stars in that area and reconstruct how much mass is there. So that's a pretty good proof, at least to an astronomer, that black holes exist. But in the future, we may be able to do better. Imagine we're able to look with an array of radio telescopes spread across the globe, so their baseline is 10,000 kilometers. Well, a group here in Europe is doing exactly that. And the hope is that when you look there, you won't see the black hole, but you'll see its shadow. because black holes may not emit light, but they do cast shadows. And so if this is possible, this would be if you had infinite resolution. The hard part is actually building something that can do this, and we will know over the next 5 to 10 years if it is possible. I see it as being quite a watershed moment if we are able to see the shadow of what we believe is a 3 to 4 million solar mass black hole in our galaxy's center. Now, cosmology is all about the biggest things, or things on the biggest scale of our universe. If we go back and say where cosmology really got going, it was in about 100 years ago. Started with Einstein's theory of gravity and the first observations. In 1929, Edwin Hubble had access to the largest telescope, the 100-inch telescope, and he was able to look at galaxies. And he was able to judge their velocity by the Doppler shift. And he was able to judge their distance by how bright stars appeared. The fainter the star, the further the object. And here is his diagram that he showed the world in 1929. And with this diagram, which shows that there's a trend that the faster an object is moving away, the further it's away, he announced that this means that the universe is expanding. Now, why did he say that? Well, let's do a cartoon. Here's a cartoon of the universe, and I get to play God because I have PowerPoint, and I'm going to expand the universe. Now, I want to compare before and after, so I'm going to take before I expanded the universe and compare it to after. And what do I see? Well, I see that nearby objects have moved a little bit. If I was measuring their velocity, they'd be moving slowly. And the distant objects, they've moved a lot. If I was measuring their velocity, they'd be moving fast. In an expanding universe, the further away something is, the faster it appears to move, just like Hubble saw. Now, Einstein's theory of gravity predicted this, but Einstein didn't realize it. The Belgian monk Georges Lemaitre told Einstein this in 1927, and actually had access through some version of a preprint of 1927 to Hubble's data, and showed that it existed in nature. And Hubble's response to him was, "Your mathematics is impeccable, but your understanding of physics is abominable." And poor Georges Lemaitre does not get the respect he deserves about discovering that the universe is expanding. And Hubble did, because Hubble didn't ask Einstein. He just put it into the New York Times. So imagine I have a universe which is expanding. Let's put it into reverse. What happens? I go back in time, and everything gets closer and closer to everything else. There is a time when everything in the universe is on top of everything else. That's the time we call a Big Bang. If the universe is expanding, it's almost inevitable that there has to be a time in the past when everything's on top of everything else. Now let's think about what that means in terms of general relativity. So general relativity doesn't say things are really moving apart. It's more that space is created between the objects. But if you go through and have two objects separated in time right now, and you look what you expect, imagine things are moving apart. They'll just get further and further apart if there's no gravity slowing them down. So I can go through and measure how fast the universe is expanding. That's the slope of that dotted line. And I can also figure out how old the universe is. That's when the two objects are on top of each other. I just extrapolate back, and I know how old the universe is. All what I have to do is measure how fast it's expanding now. But then there's this problem of gravity. Gravity slows the universe down. And if you have enough gravity, you will actually physically stop the expansion of space, and it will go into reverse. So while both those universes start with the Big Bang, only the second one ends with the Gnab-Gib, which is the Big Bang backwards. To add some extra nuances and excitement, general relativity also talks about curved space. So if you have a universe heavy enough to stop expanding so that it's finite in the future, it also, turns out, bends onto itself in 4 dimensions. Let's not worry about visualizing 4 dimensions, because I can't visualize it, and you don't, trust me, you don't want to be someone who can visualize 4 dimensions. So a heavy universe bends onto itself. A light universe bends away from itself. Triangles in the heavy universe add up to more than 180 degrees, just like they do here on Earth. Try it on a globe when you go home. Light universes, triangles add up to less than 180 degrees. And then there's this very interesting universe, which is just right, where the universe has just the right amount of stuff, that it is neither heavy or light, where space is what we say is flat, and triangles add up to 180 degrees. So, in 1995, I moved to Australia, and we had the opportunity to go back in time and measure how fast the universe was expanding. Since I'm talking Loch-Ness, I'd give you a half-hour spiel of how this works. I'm just going to give the answers today. We used exploding stars, supernovae, which we could see. And each one, we could measure the distance, and we could measure how much the universe had expanded between us and it by the redshift, how much its spectrum had been stretched by the expansion of space. That means we could measure how fast the universe was expanding to each of these objects. But because we could see these objects so far away in the past, we were actually looking back when the universe was younger than it is now. So we could measure how the universe's expansion rate was changing over time. And here is our answer that we got in 1998. Each supernova gives you a measurement of the expansion rate, and we compare the relatively nearby ones looking back to about 1 billion years in the past, so that's not too long ago, to the distant ones, which are between 5 and 8 billion years in the past. Now, if the universe was slowing down, such that it was eventually going to end and is finite, it would be following a trajectory on the bottom part of this diagram. If the universe was slowing down a little bit, but not enough to eventually stop expanding, it would be in the yellow part of the diagram. But instead, our objects were up in the top side of the diagram, where we could see that the universe on average was expanding, from our measurements, slower in the past and actually sped up. Now, it's not a particularly beautiful looking diagram, but neither was Hubble's. But from that diagram, we were sort of 99.95% sure we were right. But we were competing with a team in Berkeley who, unbeknownst to us and us unbeknownst to them, were getting exactly the same answer at about the same level. One of the participants is up here, so I have to make sure I get this right. So they also got it at about 99.95. And together, that means we're sort of in the 99.995. Still not good enough for someone working at CERN by 1/2 of a digit, but for astronomers, that's not bad. And so that was the evidence that the universe is accelerating. Why would the universe be accelerating? Well, it turns out Einstein came up with the answer in 1917, because when he used his theory of general relativity, he realized that space should be moving, it should be expanding. He didn't know what that meant. So he invented something called the cosmological constant, energy that is part of space itself. And this stuff, it turns out through his equations, makes gravity push. And by adding this stuff to space, he could counteract the attractive force of gravity, and he thought make the universe static. Well, it turns out it doesn't work. If a butterfly flapped its wings somewhere in the universe, then the whole universe started moving. It was unstable, as we would say. So Einstein's idea, we're not quite sure is right, so we give it the generic name dark energy. But it does seem to reproduce, be exactly what we need. We just need 70% of the universe to be this stuff. 70% of the universe needs to be this anti-gravity material in order to reproduce our results. Now, I would say that I was skeptical, and I was one of the people who helped make the measurements. And the community was skeptical as well, and so they did the right thing. They went out and tested. Now, there's a variety of ways you can test this. And one way started in Australia, where we did a huge map of galaxies. And you can see there's a foam structure. And that foam structure sort of tells you how mass galaxies come together. And it's very sensitive, it turns out, to how much stuff there's in the universe. A team in the United States followed suit with a much larger survey of 1 million galaxies. But they essentially give the same answer, which is that if you go through and you make a fake universe where you let the computer take gravity and make galaxies and see how they're distributed, and you have different amounts of stuff in it, different types of stuff in it, you can make up mock versions of the universe. And then you compare those mock versions of the universe to what you actually observe. And here is a good example of how this works. 4 different models of the universe, and I want everyone to look up at the observations on the far left and say, which one of those 4 things does our universe look like? Now, we use mathematical tools to do this, but your eye is very good at doing this as well. All right, so we can go through, everyone thinks, and I'll give you the answer that math tells you it looks like, which is that one. Turns out that is a universe full, dark matter, dark energy, and about 70% dark energy. So it seems to be consistent what we're seeing in this data. Now, I should say this data is not very good at detecting dark energy. It's very good at detecting dark matter. So we can do other things. The other way, and this is an exquisite experiment that nature has given us, which is the cosmic microwave background. This is the radiation of the universe when the universe was 380,000 years old. The universe is hot and glowing like the sun. It's ionized. The electrons are detached from their protons, and electrons like to scatter light. And so the whole universe is essentially opaque at this time, and it forms a screen. When the universe cools, then suddenly the electrons join up with the protons and it becomes transparent because those electrons aren't there to scatter anymore. When we look here, we are actually seeing sound waves of matter splashing around the universe. Why is that important? Because that's physics we understand really, really well. I wouldn't say it's simple, but it's not complicated. It's stuff with the right equations you can write down the solutions to and get essentially exactly right. And what's in the universe depends, the splash action, the wave action, depends on what's in the universe. So you can go through and very accurately measure how the universe is constituted. And it turns out the Big Bang, as I'll show you towards the end of this, was essentially like throwing gravel into the universe. And you got a bunch of splash marks, and you can see that wave action, and then you look at it, and you say, what was the wave action? What does that mean of what was in the universe? The other thing you can do is the size of those waves. They have a physical length in meters, because we understand the physics so well. So we can actually see how big those waves look. And the way we do that is with the microwave sky, and that Planck satellite goes through and makes a map that I've essentially just shown you, but it doesn't actually look like what I've just shown you. It looks like this. It's full of dust and other emission. It's only when you model all that stuff, junk in front, and you subtract it that you get the underlying splash marks. And that turns out to be very hard. The Planck satellite is in the middle of reducing their final bits of data, but they have made already the most exquisite map, and they will make even, hopefully, a more exquisite map in the future. So, the way that, since you know the physical size of those objects, it turns out you can measure the curvature of the universe, because if the universe is curved, it acts as a lens, and it makes objects appear smaller or larger, because the light rays have to bend on their way between you and the object. And so, for example, in this diagram, the red and the yellow lines appear the same size, but they actually delineate a different size on the ruler. It's quite akin to looking in your rearview mirror and realizing that things appear different size depending on how your mirror is bent. So when you use this technique to go out and look at our universe, what do we see? Well, we expect if the universe has the different geometries, the splash marks have a different size pattern, but we get a very definitive answer that the universe is very nearly just right. It's been born within 0.5% of having the right amount of material so that it's neither open nor closed. That turns out that goes very well with the measurements that I've already told you about, because we need 70% of the universe to be dark energy, but we need 30% of it to be stuff that makes the universe pull, and together they sort of add up to about 100% of everything. Another measurement we can do is we can look at those splash marks and realize that those splash marks are what galaxies today are made out of. And so they have a characteristic size, roughly 400 million light years or so. And so we expect to see splash marks in the galaxies today. And that gives us a ruler back then that we can compare over the marching of time. The problem is you need several 100,000 galaxies to do it. And so we are beginning to get those. And here are the initial results. And underlying these results are the predictions from the exploding star work that I have been and my colleagues have been part of. And you can see the agreement is quite spectacular. Turns out we can adjust things a little bit, and we're allowed to do that with this data. But essentially, we see the same thing. Everywhere we look at it, we get the same answer. We live in a messy universe, a universe which is 95% things other than atoms, a universe which is very nearly than a few percent, 13.8 billion years old, a universe that has just the right amount of stuff, so it's neither finite or infinite. We can't tell. It's on that knife edge. But it is a universe where we have to make up 95%. But every time we look at the universe, we keep on getting this answer. And what is reality? Reality is when you go out and you predict something and you keep on being able to predict what you see in advance. And that is what this model has done for the last 16 years. I think it's insane. It shouldn't be this way, but I'm sorry, it's the way it is. Now, we had some excitement I think, in our community when Europe decided to launch the next generation experiment to go out and map millions upon millions of galaxies with a mission known as Euclid. This mission will allow us to measure that ruler with an incredible precision, be able to measure the properties of acceleration with this space telescope, quite a small one in space, 1.2 meters in diameter. And it will also, in addition to using that ruler technique that I just told you about, it will be able to look at how light is bent by mass in the universe. And I've already showed you that how galaxies are distributed in the universe sort of tells you how dark matter and dark energy works. Well, galaxies are made out of atoms, and of course, what we really care about is that dark matter. So it's better just look at gravity. And if you can go through and you look at how light is bent by mass, as shown in this picture with Hubble, you'll see these concentric galaxies. Those are galaxies whose light has been bent by this thing acting as a giant magnifying glass. If you go further and further out, you can still statistically see that bending. And with this technique, you can measure how mass is distributed throughout the universe with an accuracy that allows you to make very precise measurements of dark matter and dark energy's properties. So the idea is if you look through the universe, light will traverse the universe, and you will end up with these little bendings that you can quantify and figure out what's going on between you and a long ways back in time. So Euclid should make the most comprehensive measurement of the gravitational effects of dark matter and dark energy over the next decade. and it will measure directly how matter is distributed with this gravitational lensing, and should use that cosmic yardstick from the splash marks imprinted in galaxies to measure cosmic acceleration. Now, one of the reasons we can do this is because we have a model which I have to admit I didn't believe for most of my early career. This is not an observation. This is a mathematical model of what we think a tiny, tiny piece of space looks like. What we see here are quantum fluctuations of things coming in and out of existence for very short periods of time on very small scales, allowed by quantum mechanics and the Heisenberg uncertainty principle. Imagine that the universe, when it was born, was full of these things, and that the universe was undergoing a time of cosmic acceleration not unlike we're going through now. Exponential expansion. That means those little bumps and wiggles would be magnified. Not by a little bit, but maybe by up to 10 to the order of 10 to the 60. So it's something smaller than an atom becomes bigger than the visible universe. That means all those little bumps and wiggles will be magnified, and there'll be new ones magnified, and you will get bumps and wiggles on all scales. Those are the seeds of what make those splash marks that I told you about. They're also the seeds that make galaxies as we know it today. But it seems like a crazy theory. It does make some interesting predictions, though. It predicts what that splash marks will look like, and it turns out it gets that answer correct. It also predicts that that magnification will cause the universe to become just right. It will flatten out any curvature. Got that right as well. And most recently, it turns out that it predicts that there will be a specific signature in the microwave background. So if you take two black holes and you have them orbit each other, it turns out that they will produce something called gravitational radiation, as illustrated in this diagram. It's quite complicated, the pattern, and it gives you an interesting pattern. Now, imagine you take those little bumps and wiggles and you magnify it by 60 orders of magnitude. That, it turns out, will induce gravitational radiation. And those patterns of gravitational radiation will be imprinted into the splash marks of the early universe. And they'll be imprinted in a particular way. Normally, most things in the universe go in and out. Gravity tends to work such that we always go in what we say a radial direction. We tend to always things work in and out. Gravitational waves, on the other hand, work that way as well, but they also work in a way that they can produce spiral patterns. And that spiral pattern in the early universe is almost impossible to produce in any other way. So there's a very strong prediction that you should see spiral patterns left over from this era of what we call inflation. Bicep 2 earlier in the year made this diagram which said we see those spiral patterns, and that tells us we're looking at the imprint of the universe when it was 10 to the minus 30 seconds old. The problem is that the signal is 1 part in 100 million. And you have to worry about everything. And one of the things you need to worry about is this dust. Unfortunately, they were unable to make their own map of dust. And we are all waiting now for the Planck satellite to tell us what that dust really looks like. And my understanding is that answer is imminent. So we will see. I am hoping that the Bicep 2 team has got it right, even if maybe they were a little lucky, because if we can see this signal of spirals, that means we have a chance to look at the universe when it was just that tiniest of a second old. If we can't see those, it's all sort of a quasi-well hung together story that you can't easily test. And if you can't test it, it's a nice story, but it ain't reality. All right. So The cosmic microwave background is really the gift that keeps giving. I'm not sure what it's going to do in the future. We keep on thinking we've tapped it for all it can give, and it keeps on surprising us. But I do know that if you can go through from a time 10 to the minus 35 seconds to right now, in less than 100 years, and understand that entire dynamic range, you've really done something. But I also know that from young planets to the distant galaxies that I haven't really had a chance to talk much about, we're going to be able to use the James Webb Space Telescope. We're going to be able to use the next generation of large telescopes, ALMA, to look back and literally see how stars and galaxies were born out of the Big Bang. We don't know much about that. We don't know much about the universe when it's 10 to the minus 35 seconds, but we know some things. And so from young planets to distant galaxies, I think there is no doubt that we're not in the position in 1905 when everyone said we've learned everything. Quite the opposite. We know much more. We have many more questions that we have answers. And I'm still impressed at how many answers we do have. But I'm also impressed at how much we do have left to answer. So we are still a frontier science, and I pray that it will always remain that way. Thank you very much.
Thank you very much, Brian, for a whirlwind tour through most of the universe and time. We had a number of questions from Twitter, and I may add one myself as well. We'll see. Some of them had to do with BICEP 2, but you covered that all the way at the end.
Yep.
So I will not go over that again. Somebody asked, what about building a telescope on the moon? Is it possible inside 20 years?
So it would be really, actually my undergraduate supervisor, his big plan was to put a telescope on the moon. Imagine you put a small telescope on the moon. What do you have? You have a very dark site. You know, no lights, and indeed even the Earth is in shadow. So that's useful. You have an object that orbits about it, so it essentially rotates as it goes around the Earth, so every 29 days or so. So you can imagine just sitting it there, staring up at sky, taking images as the sky goes past. It would be a fantastic sight. It would also be fantastically expensive.
Yes.
And so I think if we wanted to do it in 20 years, give us $20 billion. I don't know, we have NASA people. And how many billion would it cost for NASA to put a thing on the moon?
I think it'd be more like 100.
100 billion, okay.
Yes.
Well, we need a lot of money, so.
Very good. You didn't mention, so you mentioned lots of telescopes, optical infrared, radio, satellites, etc. There are also particles coming from the universe, which we can detect with some angular resolution, so they come from objects. Do you see anything useful there?
Yeah, so one of the things that we've been able to do over the last 20 years is that there are places that produce incredibly high energy particles that are, you know, almost like a baseball or a cricket ball, as I would say now, in terms of their total energy, all in one tiny little photon. How they're produced is a bit of a mystery, but you can go out and you see them where you actually use the entire Earth's atmosphere as the detector. And they come in and they interact and they produce a whole shower of thousands or tens of thousands of other particles. And you look at that shower of light as it comes down, and you can figure out where it is and how much stuff there is. A particular version of this program in Namibia, HESS, European-led, has really been able to go out and start mapping things this way. And you know, it is very interesting. Still early days. It's
yes.
hard physics how you produce this. But it might be one way you would detect, for example, dark matter. We think there's some chance that dark matter might occasionally produce a very high energy particle, and you might be able to map it out somehow using a technique like this. There are also other things of just understanding how these particles are produced. It's really physics in its most extreme form in the, much more than we can even do within the Large Hadron Collider.
So it's again frontier of science. I think the final question is again a tweet which connects a little bit to this, since you mentioned dark matter. And the question is, what if dark energy and dark matter have the same origin? Is that possible, a dark fluid?
Well, that would be really good if someone could come up with a sensible theory. Yes. So the problem is not lack of theories. There's about 7,000 or 8,000 theories now on dark matter and dark energy. The problem is we can't tell any of them apart. Probably all of them are wrong, or maybe, who knows, maybe one of them is correct. The problem is it comes down to what's reality. You've got to be able to test it. You also need to differentiate. If you have 5 different ways that all give the same answer, but they're all physically very, very different, that really does confuse reality, even for me, who's pretty philosophical about it. So I would love for there to be a theory that combined all of this, but there's no real reason. It would be nice, but there's no real reason to believe that it has to be that way. But we will wait and see. We're waiting for the next Einstein out there to come along and produce some brilliant vision of how this universe, which is pretty preposterous when you really think about it, actually works.
Right, and I think this is quite an interesting topic to end on. Some theorists like to play tennis without a net. It's very easy, as most of you know. But what you showed in your talk, even for Einstein, it's extremely important after you've developed this theory that you go and test it and that it fits everything you can observe and continues fitting it. So keep doing better observations and use our brains. I think we should give Brian, also given the time, a mighty round of applause for a wonderful lecture, and he'll be here.